Hello, everyone, and welcome to our webinar, Beginner's Guide to Vector DBs with Tom Ye. My name is Matt Brown, and I'll be your moderator today. One of my jobs at SingleStore is to organize these weekly AI webinars, 2 per week, demoing data and AI use cases, new tools, and new technologies. I post about these upcoming webinars every week. So if these topics are interesting to you, feel free to connect with us on LinkedIn to stay in the loop. I also love to hear your feedback or any ideas that you have on future sessions. Speaking of future sessions, we've got another great session coming up just tomorrow. Tomorrow, we're going to be presenting Claude 3 Cookbook, leveraging OCR and multimodal data extraction. You can come see a live demo. It's really cool. Claude 3 has some upgraded functionality on looking at images, documents, and sort of grasping, even when they're complicated with different arrangements, different layouts, different text and graphics. It's very good at grasping it, the way a human would. So come join us tomorrow. We're going to do a demo and code share. Hopefully, we will see you there. Back to today's topic. We would love for you to participate in the Q&A discussion throughout the session. There's going to be a Zoom Q&A at the bottom of your console. We have an internal mission statement to try to answer all of the questions that come in, even if we have to follow up with some folks via email afterwards. Please make sure that you have logged into your Zoom with your name and email address, because we won't be answering any questions from anonymous users. Also, Tom sent a PDF guide follow along for today's session, which we emailed to all registrants this morning. In case you missed it, I'm going to post a link to it in the chat. Take a look at that. Feel free to follow along with that PDF as we go through the slides today. And then one final note, we would love for you to try out the technology that we're talking about today. In fact, anyone who tries it for today, anyone who tries it today will be entered for a chance to win free new AirPods Pro or Meta's new LLM smart glasses, the Ray-Ban smart glasses. It's your choice. If you're the winner, you can choose either prize. All you have to do is visit this link that's on your screen. It's the Beginner's Vector DB raffle. I'll put that link in the chat in a minute. You just have to log on. If you already have an account, just log in to SingleStore. If you don't have an account, we have a free shared tier. So you can try it out, play around with it for free. We'll talk a little more about that free shared tier in a second. Let me quickly introduce our speakers. Akmal is a senior technical evangelist at SingleStore. He has strong expertise in big data, machine learning, and AI. He's a regular speaker at our webinars, and so you might already recognize him. And then Tom is an associate professor of computer science at the University of Colorado Boulder. Tom received his PhD in computer science from MIT. We found him online after his posting of several viral posts explaining vector databases, neural networks, and other AI and machine learning concepts, all drawn out by hand. Very cool content. So welcome, Tom. Welcome, Akmal. Akmal, I believe you have the floor first, so I'll give the mic to you.
Great. Well, thank you all very much. And thank you for joining today. So I'll be short because Tom's got a lot of great stuff to get through. And so I'll say a couple of words about SingleStore. Okay, so just a little bit of history about the company and the product. So this is always a nice slide. This is a kind of a new one that we have. Just shows in terms of the growth. So we started way back here, 2011. And originally, both the company and the product used to be called MemSQL. Okay, subsequently added support for columnar data, analytics. And then, as you can see, there's a couple of kind of inflection points there. So here, round about between 2017, 2018, that's where the revenue really started to increase significantly. And then between 2019 and 2020, the number of customers started to increase significantly. So currently, as we are today in 2024, we have over 100 million in annual recurring revenue, ARR, and over 350 customers. Many of those are global names, as you can see just below there. So that is a little bit about it. So it feels like working for a startup. Everything's 100 miles per hour, but it's an awesome place to be. Okay, and just a couple of words about the product itself. So architecturally, it is started obviously live as a database system, but it is now a data platform because it does much more than that. And I mentioned the in-memory and the analytics capability. So now this is achieved through this concept of sort of universal storage, a single table type that can handle both OLTP and OLAP. And so we integrate with lots of these awesome technologies, things like Kafka, for example. I've been writing a whole bunch of articles on Spark over the last week or so, looking at how you can integrate various technologies and actually run Spark in our very own Jupyter notebook environment. Other things, Hadoop, HDFS, okay? And we have this ability to ingest data at scale, okay? This is what the animation is showing here, this thing called pipelines, which we've demoed many times in our webinars. So Matt mentioned the link. Please sign up for that. You will get access to the portal, and that's probably the quickest and easiest way to use the product, nothing to install locally. And so we do run on the 3 major cloud platforms, AWS, Google Cloud, Microsoft Azure. You can run it on-prem, okay? That's possible too. We have some customers that do that. There is a Docker container as well. But seriously, the quickest and easiest way, I mean, literally, it's less than a minute of your time for the AirPods Draw. I mean, if you follow that link, it'll take you a page and just sign up. Either use Google or Microsoft, or just enter your username and create a password, and you'll get a link to that. In terms of the data types, well, obviously relational historically, that's been the mainstay, but the product does far more. Recently, for example, I've been looking at geospatial again. It's something I covered in the past. We do things like time series as well, JSON support. And today's kind of this topic of discussion, vectors, okay? So the product has actually had vectors since 2017, although earlier this year, lots of great new stuff added. So a dedicated vector type, and things like approximate nearest neighbor search, and lots of ways to do that as well. Okay, so the documentation covers that in detail. So just wrap up here, last kind of remaining bits here. So machine learning dashboards, we have the notebook environment that allows you to create these as well. So if you're familiar with Matplotlib, Plotly Express, for example, these are technologies I use very frequently. Or even if you use things like Tableau, for example, I use Metabase, free version. This is just a jar file. And then within like 2 or 3 minutes, you can be creating pie charts and other types of animations, illustrations, things that allow you to analyze the data. Okay, just briefly then, just to say that some of the ways that we could work with utilizing machine learning with SingleStore. I mean, this is not an exhaustive list, okay? So some of these I've mentioned already. And one thing that I think I should have added to this, Matt, is pen and paper or pencil and paper, which is what Tom's going to show us. And so Tom's focus is very much on looking at a lot of the concepts behind many of these sort of capabilities, things like vector support, for example. And so he's going to go into that in detail. And we often get asked questions about this on these Q&A in terms of the webinars. So sometimes it's great to just take a step aside. I was going to say step back, but in fact, it's not, okay? Because you are just looking at things in a slightly different way. And it's great to just be able to think about a problem with a piece of paper and a pen and be able to figure that out. And once you understand those concepts, the technology is easy or can be very easy, okay? And so with that, I will stop there, okay? And so Matt and I will jump into the Q&A, and I will stop sharing now and then hand over to Tom, and Tom will take it from here. Over to you then, Tom.
Hello, everybody. It's a pleasure to be here to talk to you about vector databases. And I want to thank Matt and Akmal for arranging this opportunity. And so I'm gonna take you through is a guided tour of beginners concept about vector databases. I'm going to use my pen and the drawing tablet to solve a lot of a series of exercises I prepared. And I would like to encourage you to download the PDF. If you have already printed, you can follow with pen or pencil. If you can also use tablet and to use a tablet pen. And if you don't have access to a printer nor a tablet, and I also like to recommend you could follow with your finger trace. It's basically, this is very hands-on, but we are using hand on paper, and hopefully they could help you learn some of the concept we're going to go through. And I'm going to start screen share so you'll be able to see my slide. And also I'm going to turn off my camera so I can maximize the bandwidth. And so you could focus on the screen share. All right. And I'll see you again at the Q&A session with my camera on. Okay. So my name's Tom Ye, and I live in Denver, Colorado. So I work at the University of Colorado Boulder. So this is my university's name and I live in the city of Denver. And today it's sunny over here. We have more than 300 sunny days per year. And my son, Isaac, he's 6 years old. He's at a school just not far away from my home. And so I'm doing this webinar from my home. It's pretty quiet. Anyway, so today's plan, the roadmap of today's lecture is I'm going to start by just a little review of what the database is and how can we add, and then we'll talk about how we can add vectors to the database and how can retrieve the records from the database, and how does dot product work, and how to go from dot product to word embedding, and how do we go from word embedding to sentence, which a sentence is a series of words, and how can we search a database with lots of embeddings. And if we have time, we can talk about some transformer, and then we'll have some question answer at the end. So this is a roadmap. To start, I will start with the database. Just database is where we are now. And so I mentioned my son Isaac. A couple days ago, he asked me, Dad, can we get a dog? Why do you want to get a dog? And he told me that almost like everybody in his class has a dog. They made me wonder that, there are a lot of dogs in the world. So just how many dogs are there in the world? So I did a little research on the internet. I found that there are just 900 million dogs in the world. It's almost like 1 billion dogs. There's lots of dogs. It's a fun fact that I'm gonna start with. And we have lots of these facts about animals. Suppose we'd like to create a database and we can use SQL. SQL is one of the most common programming language for interacting with the database. And so we want to create a table. First, we want to create a table, and just as for some of you who are familiar with SQL, so this could be a review. So how do we create a table? How do we write a SQL? What's the command for creating a table? The hint is in the sentence, create. So we do create a table, and then we'll pick, we have decided the names of the table. So I want to call it animals. So I write this create table, name animals, and actually animals. And then I did this table. There's going to be some properties, and it looks like columns. So this is the shape of the table in the bottom I want to create. And so I have ID, name, and size, and pump. And one decision we have to make will be that the data type for each of these property. So for ID, we typically use the integer. So I write integer. And for name, we typically can use a variable characters. And then we get to specify how many we want. So it says 10. So cat, dogs. If we have animal names really long, might not fit, but that's okay. And the size of the animal big. So maybe I use the integers to indicate 1, the kind of small, 2, medium size, 3, pretty big, and 4, enormous, and so on. And population integer. So with this command, with this SQL command, we send it to a database such as a SingleStore, or you can host it with MySQL on your own computer, and you create a table like that. And the next thing we want to do is to insert a record into the database. And what is a SQL command to do that? The answer is insert. So we'll write insert here. Insert into the table's name animals that we give on the previous slide. And they won't also need to use a keyword to indicate we have one dog to 900 million that I want to add into the database. What will be this keyword I have to put it here? Values. All right. So this is the command we'll use. Insert into animals values and parentheses and 4 different values and add that match the 4 different columns in our database table: ID, name, size, and population. So this is how the traditional database work. Next, I would like to move on to talk about how do we add vector into this traditional SQL table-based database. So how to create a vector database? You see the similar syntax. It's the same syntax that we just went through previously. And then if we would create a table animals with ID, name, size, and population. So what I'd like to add is this new column called embedding. It could be, you could call it a different name, but then I just, for the purpose of this lecture, I just call embedding EMB. And so instead of integer, varchar, and we'll have a special data type we can use. It's called vector. It's pretty straightforward. We can use vector data type. And with vector data type, also take a parameter here. So you can decide the size of vector. Vector is a sequence of numbers. So you get to decide how long you'd like that sequence to be. So in this case, suppose I say 3. And then in here, they will create like a storage for storing exactly 3 numbers, which is a vectors under this column. So that's how we'll create a vector database in this case, but adding a property, a new property, which is a vector of a particular length that you specify, in this case is 3. And with that, now how can we insert a record with a vector? So this is also following the same syntax that we worked through in the traditional database example. And the only thing that's new is that we'll add a vector to the 5th property. In this case, just as a demonstration, suppose for this animal dog, a particular vector representation embedding is 2, 1, and 0, because we specified earlier we would like this vector to have a length of 3. So that's why I have 3 numbers. And 2, 1, 0 going to come from some other mechanism I'm going to cover when we talk about word embedding later. So once we have this command, then you submit it to your SQL database, and then our vector database, and you could get 2, 1, 0 just inserted right here. And you can keep repeating this process for another animals, for cat, for cow, for lion, elephant, and so on, following a similar syntax. Okay, so that is okay. And so then you saw how we just add vector to a traditional database in this way. And how can we retrieve from it? What is the command for retrieving from such database? So suppose we have a query in this animal, and we are interested in the table to the right. This is a vector database table. We have 5 columns. The last column is embedding. That's why we already looked at. There are 2 different animals, dog and cat. Our query is, dog and bat. They are in the database. So our query is cat. And suppose there's some process, we can actually get a vector in representation for a cat as well. So in the query, we have this word. We also have a vector representation of the concept cat. And so how can we retrieve something that's relevant to this query? We have 2 options. One is that we could just match the cat to this name column. So in this case, we'll retrieve which of the word is closest to cat. In this case, you probably will say bat, because bat and cat, they only differ by 1 letter, and B and C is only differ by just 1 character in the alphabetic sequence. So you probably retrieve this, but that's not what we want. What we want is to retrieve dog, because dog, it's just in my mind, they are both pets, they're about the same size, they're all cute, so they're more similar than cat and bat. So we might want to match embedding over here and to be able to retrieve dog instead of cat. So that's how conceptually we want to be able to accomplish in our retrieval process. All right. Okay, let's look at the next slide. And to do that, we have to think about, well, is cat, I've been using this term similar or close kind of loosely, but in a high level, what want to do, the relevance could be defined in two ways that we can talk about, well, which record is cat, which animal is cat the closest to? When we talk about close, that is a notion of distance. Or we can say that which animal is cat most similar to? When we use the word similar, so it's a notion of similarity. And then there's a really easy way for me to draw distance versus distance versus similarity in this way. In this exercise, that one way we can draw distance is we could consider the center of these two circles. So we have two circles. We want to talk about the distance or similarity between the two circles. For distance, I could draw the center for two circles over here, and this thing is the distance. Okay, this is how we draw it. For similarity, on the other hand, I will focus on the overlap between the two circles. So I would draw in this way. So this similarity. And with this is how I will always remember how similarity and distance contrast. One is the distance. The other is how much it overlap. And with that, the next exercise is that I would like to ask you on a scale of 1 to 5, can you put distance and similarity on this scale? So on the top, I have similarity. At the bottom, I have distance. So I start with similarity. I use this color pen to draw similarity. And so to draw similarity for the first one, so the similarity is the overlap. I kind of color the whole thing. There are two circles are overlapping. The second one, the overlap gets slightly small, but still big. And then this overlap and this overlap. And the end is no overlap. So if I would like to put a scale on a scale of 1 to 5 for similarity, and the first one, because it has the biggest overlap, I drew a lot of stuff, so it's 5. And similarly for 3, 2, 1, it go this way. And let's consider distance. If I draw distance, so the distance between these two circles is like nothing. I can't even draw it. But distance between this one is this between these two. And for this is between this and between this. You can see that the line I'm drawing is getting larger and longer. So if I put it on a scale on distance, I will instead put 5 over here, 4, 3, and 2, and 1 over here. So once you see this, so I would like you to circle, think about the sequence, the ordering. There are two different ways this number can be ordered. So and this is ascending or descending order. So in this case, 5, 4, 3, 2, 1. Is it ascending or descending? As you can see, it is descending, right? Descending. And for the distance, on the other hand, the ordering is 1, 2, 3, 4, 5 is ascending. So once you see this difference between the two, and that you could probably answer my next question, which is how can we retrieve by similarity? So there's a special syntax, extended syntax for SQL, and that's supported by database vendors such as SingleStore and some other vendors. And so you could do a select, which is a typical syntax for SQL to select, but select a name of the animal, cat and dog. And with embedding, we're going to look at embedding the column. Suppose we have cat. The embedding, what is the embedding for cat? Let's go back to 3 slides. It's 1, 2, 0. So I'm going to fill 1, 2, 0 over here in this template as score from the animals tables. And then I would like to order them. So order them by a particular ordering, by a particular field. So I'm going to assign this to a score. And so by score, And this is the most important thing. Is it ascending or descending? I have a little typo here. Do you remember dot product similarity? I say similarity. One way is to calculate similarity through dot product. We're going to talk about dot product next. But similarity, do you remember is ascending or descending? Let's cheat a little bit. The similarity is descending. So I will circle descending, but I'm not gonna do ascending. So that's how we do. And for dot product, to compute dot product, so one symbol is this star sign. So add the star here to indicate that it is a dot product we are trying to do. So dot product is similarity, and similarity is supposed to be in descending order, so you can get something that's most similar. Something most similar is something that have a most overlap, and you can picture in your head something kind of bigger and larger. So that's why we want descending order. On the other hand, if we switch to the distance part, and so one most popular is called Euclidean distance or L2 distance. And how to retrieve by distance, let's update this code. This is the same code I just copied from the past. We need to fix a couple spots for that in order to change this to be able to retrieve by distance. Where do we have to change? First, we need to change this from star to another symbol called minus. So distance is 1 minus something, a minus b, and take the absolute sign. This is how we calculate distance. In algebra. Something else needs to be changed. This has to be changed to ascending order. So by making these two changes, so we'll be retrieving data by distance from using Euclidean distance. Okay. All right. So this is how we retrieve records, a typical syntax using SQL like syntax to retrieve records from the vector databases, and there's a very subtle distinction between distance and similarity you have to be really careful about. Now let's talk about dot product. How do you compute dot product? Getting a bit more math here. So to compute dot product, then we have, I'll start with a really simple example. So I have two vector. One is each vector has 3 elements. To compute dot product, we'll multiply each element and add them up. So suppose we have dog and cat. What dog is 210, cat is 120. Those are numbers I gave you earlier. How do you calculate dot product? 2 times 1 equals 2. 1 times 2 equals 2. 0 times 0 equals 0. And then we add this up. 2 plus 2 plus 0 is 4. So this is the result of the dot product. And that is a really good estimate of the similarity between two vectors. Be careful, I use the word similarity. If I use the word distance, I was actually mistaken. So this is a similarity matrix. And another way to calculate dot product, which is my favorite, is to use a matrix multiplication representation. So nobody really likes to multiply matrices, but multiplying matrices is really important if you really want to understand how deep learning neural network work. This is a core of mathematical operation. And my favorite way to visualize and also operationalize matrix multiplication is to arrange two matrices in this way, kind of in the offset, in the cross intersections of the way. So instead of putting it side by side, like in parallel like this, I like to just turn one around to get this way. And in this case, I could just do this 1 times 2 and 2 times 2, but 3 times 0 is nothing, so I don't have to draw anything. So 1 times 2 is 2, 2 times 2 is 4, and like over here, a sum over here, I get 6. That's how we'll compute this. How do we do dog and cat? So we'll do this 2 times 1 is 2, 1 times 2 is 2, and sum, I get 4 over here. So this will get exactly the same result, but this particular matrix multiplication is very scalable. Once we have a lot of animals we have to match, a lot of record in the database we have to compute, you could do that with a matrix multiplication, which I'm gonna show you. How do we compute dot product with multiple vectors? In this case, so the first is first we just did get 6, but second we repeat exactly the same thing. 1 times 2, 1 times 2, but 1 times 0 is nothing. We're not gonna draw. So 2, 2, sum, we get 4. Okay, let's compute a second column. How do we compute the dot product between cat and bat? Remember, if we only look at the alphabets, they are really similar, but now we want to compute the dot product. Let's see what the dot product tells us. Is it higher than 4 or lower than 4? So let's see. 1, 0 can ignore. 1 going times 2 is going to be 2. And 2 times 0 is we can ignore again. So in fact, gonna be 2. So in terms of similarity, we want larger the better. So in this case, it's actually not a bad embedding because bat and cat, the dot product of it is just smaller than dog and cat. And we want dog and cat to be more similar or higher similarity values. All right, so that's how the dot product work and how it could be an estimate for similarity. Let's talk about word embedding. So suppose we have now I would like to use a more abstract representation of the space, the concept of the space. And space, we can allow you to think about similarity if they are closer, they are overlapping similarity, or they are distant, they are really far away or close to each other. So where you are to consider this space, we just consider the name, which is dog, cat, and bat. If we just only consider the namespace in terms of English, I would probably two of them are a lot closer or a lot more similar to each other than the other one. I will argue that cat and bat should be closer in the namespace in this particular embedding, and because they only differ by 1 character. And dogs should be far away. But usually that's not what we want. But in the traditional database, that's what we get because we can only search by text. And in vector database, we could get around with this by having a different representation, different embedding. And in this case, we'll go to see this one more time, but instead of namespace, how about let's think about semantic space, the meaning of these animals, the property of this animal, the semantic space. In the semantic space, we like cat and dog to be the same because they are just kind of cute together. And then bat would be further away. And so we have 2 different spaces. We can have 2 different embedding spaces to represent each of this name or semantic space. Now, I'd like to just talk about how do we determine which spaces are better? Suppose we have 2 different schemes to embed for embedding. Which is better? We have 2 ways to represent dog by just a bunch of numbers. Embedding 1, embedding 2. One is highlighted in yellow, the other one's highlighted in green. How can we tell which one is better? How can we tell the other one? How do we do that? So one way to do that is that, well, we have some kind of knowledge about our desired dot product similarity. We could just compute a dot product with every single pair. So look at the gray one. If we put it together, we have a matrix representation multiplication with dog cat bat with dog cat bat on its own, just like kind of rotated. One is rotated. But then the desired dot product, dot product similarity is that we want dog and cat. This is the dot product of between dog and cat here. And want this to be high. And this is a dot product between dog and bat. We want this to be low. Okay, and then this is a dot product between cat and bat. We want this to be low too. And for this matrix, they are symmetric in the way that dog and cat is the same as cat and dog. So this is high. This is symmetric. High, high, low, low, and low, low. So the symmetric. That's what we want. So we will compute the dot product for these 2 in this way. So for this one, let's just compute this, and this. What do we get? We get 4. And for this, again, this, what do we get? So we get 0, 0, nothing, 1, and 1. We get 1. And then this one, and this one is cat and bat. So we get this 2, we get 0, 0, nothing, 1, 2, we get 2, and 2, 0 is nothing, so we get 2. And now, knowing that it is symmetric, so I just copy 4 over here, copy 1 over here, copy 2 over here. So now we have this like matrix that was pairwise comparison between every single animal in our database. Even though our database is small, only 3, but you can consider we have 100 animals, we get 100 by 100 matrix like this. Or 10,000. So it can scale up. Let's look at another one here. So cat and dog, in this case, we get only 1, and I can fill out the value. And this one, 102 and 210, we get 1, 2, nothing, nothing. So we get 2, and this one, how do we get? 1, nothing, 0, 1, nothing, 2, 2, 4. So now I could do a symmetric operation, 1, 1, 2, 2, and 4, 4. All right, now we have 2 different matrices. We can compare them. So we have a green and yellow. Is green an improvement or not an improvement over the yellow? So look at it, which one is closer to this high-low matrix over here, this target? Then you can see that the green is better, right? No, it's actually yellow is better. See, high, low, low. But this is not this high, low, low. This is actually high, low, low in this way. So in this case, we know yellow is better. So there are some machine learning algorithm for you to keep trying different embedding and updating some embedding numbers and keep improving this until we get the better and better matches our desired dot product similarity, this which our desire. And then we keep doing this process, we get a really good embedding. All right, so this for how we can get kind of high level intuition, how we could say one embedding is better than the other. If we can say one embedding better than the other, we could just keep improving the embedding until we have embedding that work for our application. And in practice, usually embedding will be kind of something you can download from like Hugging Face and some repository, because companies have spent lots of resources to train them and share with everybody else. Now we've talked about word embedding. Let's talk about how we can combine it into a sentence embedding. So then think about, instead of just cat, dog, and bat, just one word, let's think about sentences. Consider this different application. We have sort of a comment database. We have user, we have comment and ID, and the embedding. How can we compute embedding from individual word, but we can get just one embedding for each sentence? So let's look at this process. The first is that we given a word, how are you? A sentence, how are you? There are 3 different tokens, 3 different words. And we can get the word embedding vectors. So each word, suppose we have this embedding, and then we have some process, some machine learning process to already give this embedding is kind of optimized for this vocabulary. Following a similar logic that I showed you earlier, let's keep improving it until similar words are having higher dot product value, and until we couldn't improve anymore. Suppose this is given, and with how are you? So I do some loop dot how here with 1 0 1 2 1 0. So I kind of write it down here. So this is how are, I'm gonna look up somewhere here. So R, I looked up here. So there will be all looked up operation. There's not a lot of calculation. Calculation be already done. So U is somewhere here, U. So I looked up U and we'll get 0 1 0 0. So I'm gonna look at this. So I start with 3 words or 3 tokens. I end up with 3 column vectors. Each column vector has 4 numbers. So this is 4 length of each embedding vector is 4, but I can look it up in this way. So how are you get the word embedding vectors? And before we can store that in the database, we tend to just store 1 vector. So we have to combine the 3 vectors into just 1 vector. Combine 3 word vectors into 1 sentence vector. Method 1 is we can concatenate them. We can just concatenate, for instance, we just write down 1 0 1 0, which is the first column, and then add 0 1 1 0, which is the second column, and then 0 1 0 0, which is the third column vector. And then we have this one sentence vector. And then it will work in some cases, but it might not be scalable. We have, instead of having 3 words, we have like 10K word tokens. Now, large language model have higher and bigger and longer context window. We easily can get 10K, 100K tokens. It's just the concatenation not gonna work, okay? And so, and usually the method 2 is more preferred and simpler, that we could simply take an average of the two, but combine them into one vector of the same dimension. The dimensions, model dimensions 4. So we combine them, we take an average, would be 1/3. 1 plus 1 is 2/3, 2/3, and 0/3. So now we have this is our sentence embedding vector for how are you. So I write it down and store this using the syntax we covered earlier. So I can write down 1/3, 2/3, 2/3, and 0/3 in this. So this is most likely we'll use vector for data type to get this embedding column. Okay, and then this is taking average, pretty commonly used. So but then you could also use some other things like transformer. If I have time left, I could go through transformer real quick. All right. Let's try a different word. Just repeat this exercise one more time. How can we apply to who are you for word in converting into word embedding vectors? There are 3 vectors. So are you part is exactly the same as the previous example, previous sentence. So I just already had it written down here. The only new words who. So who, we're gonna look that from here, come down over here. So who is 1, 0, 0, 0. And this is another practice. How can we then convert them into a single sentence vector through the simplest method, which is average? So it's going to be 1/3, 2/3, 1/3, and 0/3. And then we'll store that into our database here. So it will be 1/3 here, 2/3 here, 1/3 here, and 0 over here. Okay, so you can always already kind of eyeball that. It's actually this, if you look at embedding, if you take a dot product between the two, they're quite similar. And because how are you and who are you are quite similar anyway. And then with that, you can imagine a process of we could turn lots of comments into each comment into its own row. We can just run this in the loop, just keep adding more into our database. We have a really large database with these sentence vectors. Okay. And so how do we query this? So this is a review again. We looked at it already. So how do we query the database? We use the SQL command, SQL command called select. We select. Now we can select from this table, select this table. And then let's see. Let's just do similarity. So with similarity, we have 2 symbols to choose from. This or this. Which one should we choose from? Turns out we'll use this one, dot products. And then embedding, take a dot product with a vector. So suppose the sentence we want to retrieve, we can just, and then there's some process for us to get embedding. We get embedding, say 2/3, 1/3, 3/3, and 4/3. And then assign this to as a score. And from a new table called post or comments, this is a post with an order by the score. And this is, again, a review for similarity. Dot product is ascending or descending order. Think about it for a moment. Think about 2 circles overlapping. Do you want it to be big or small? We want it to be big and going down, so the descending order. But that would be a correct syntax. And if you got it mixed up, you do ascending, you're gonna end up returning the least similar records first. That's what you don't want to do. If you find SQL is difficult to write, and there are various options for high-level API, and one of the things I'm familiar with is from the superlinked. So this is one of the Python API that usually look like this. So you can define a query and give it the index, and you can say, I like to find stuff based on not distance, but based on similarity. It's going to build some build the right sort of SQL for you and query the database, and you can specify that I would like this to be about the comment field. So when you build an app, there's an app.query, and you can give a query, and you could populate this query with comment, which is a field I would like to query on. And the query text is who are you? And the some complexity of mapping who are you to embedding space following a similar process I show you, will just be computed, all kind of hidden underneath this high level API. But now, hopefully, as you follow through my lecture up to this point, you have opened up the black box and you can see what's underneath this high level API, even underneath the syntax, is really big dot product operation, or some and also embedding operation, and merging the embedding into a sentence embedding. Let's talk about search. So suppose we build a really large database. In this case, I have a simple database of 20, but you can think of this principle gonna be applicable for 20,000, 20 million records. Now I have 20, in this case, 20 records. I have a query. I just visually represent it's a 4-dimension in each embedding vector. So I have a query. Suppose I take dot product, and this is the result. Now I want to find the top 3, and using the k nearest neighbor, k equals 3. So how would you do that? First, you have to decide for dot product again. Do we want max? Do we want mean? Do we want big? Do we want them to be big? And the answer is yes, we want them to be big. So I will circle max to give you an idea. So I want to find the maximum of some of the dot product value. You can notice that there's some minus because dot product is possible to be negative. And then to find the max, they're going to go down, scan down all these numbers. So start with 9. That's kind of big, but I'm not really sure. Is it the biggest one? We don't know until I scan down. I'll find 11 pretty big. Is it the biggest? I don't know. 13. Oh, 15 even bigger. Okay. Yeah. So I scan down to the end. I'm pretty confident 15 is the biggest. So this is my number 1. So I circle out. And second pass, I have to go down all the way to the beginning and to try to scan one more time. And I find 13 to be the second largest. Then scan again. Now find 11 to be the third largest. So in this case, for dot product, the k nearest neighbor, it could be computed in this way. Scan 3 times. It's a naive way. There are some other more complex algorithms. And for the L2 is a distance matrix. So suppose we compute L2 instead. Remember using this expression. And we're going to get a different set of numbers for this. And you can notice that now this number is negative because distance is supposed to be either 0 or positive. It cannot be negative because of the math. And for distance, do we want to have minimum or maximum? So in this case, we want to do the opposite. We get a minimum. So, but the process is similar. Is 6 small enough? We don't know. We scan 1 pretty small, but it could be something smaller down the road. 0 is as small as possible. And usually you get a 0, we know we cannot be doing better than 0. So this is top number 1. I do this again, scan again, and find this one to be second place, scan again, this one to be third place. You can see that as I'm scanning, it's kind of slow. Also, do we really have to compute all the distance between every single pair? But in the naive brute force, k nearest neighbor, that's what you have to do. So 20 is fine, but what if we have 20k or 20 million records? So we need an algorithm that we don't have to scan the whole thing. We could just only scan some of it. And then when you do that, it will do this thing called ANN. In this context, it does not stand for artificial neural network. It actually stands for approximate nearest neighbor in this case. And then there will be its own lecture to talk about if you are interested in intricate math. And most of the vendors are supporting this ANN efficient algorithm under the hood. So you could you can retrieve your data a lot faster than having to scan the entire database. All right, now we do have time left. I could quickly give you a 5 minutes overview of the transformer process, but how does transformer really work? So, and Earlier on, I talked about the need to combine all the embeddings in vectors into one sentence embedding vector. And the most naive way is simply combine them, take average. But this is not what we do in the practice. In the practice, we use a model like transformer to extract some features, and then we just pick one feature at the end to get one vector of this, hopefully the same size, easier to index. And so I give you just a feel of how the transformer work in this case. So how do you, so first that we'll like to combine, this is like a word embedding vectors, three words, if I remember, to combine, we can combine across, there are three different positions. To combine across the position, so we'll put this matrix to the top over here, upper right corner. So when we do that, when we compute this, one way we compute this is that we have one, we usually map to here, another one map to here. So this +1, +1, and then this result will be adding these two columns together. So 1, 1, 1, 0. This is how one way to calculate it very quickly. So combining across position, basically you can think of this one is a combination of the first column and the third column. And this is sort of like a attention matrix. It tells you this, you should pay attention to the first position. Also pay attention to the third position, but you pay no attention to the second position. Same logic for another feature. Suppose we want to derive another new feature based on the across positions. In this case, so I have the second and third to be 1, so map to this one. So this what is it telling me is that, hey, you should pay attention to the second and third position, not the first one. So as a result, combine these two columns, we'll get 0, 2, 1, 0. Repeat this again for third one. Where does it say? You look at this yellow one. Which position is it asking us to pay attention to? If you answer the third position, you're listening, you're on track. And so this pay attention to here. And so only one. So in fact, it's just exactly the same as the third column. So this is a result of combining across position. We get 3 derivative column vector. Each one is a attention weighted vector. We call this an attention weighted vector. So we can repeat this process by across a different dimension, kind of vertically across the rows. This will be combining across features. In this case, I have this matrix that you can you put it on the lower left corner of your feature matrix. Well, I still have 3 different positions, 3 different word embedding. But in this case, look at the weight. We'll have 1 and -1 and 1 and 0 is something we can ignore. So 1 map to the first row, and this match the third row. And this one in the gray area is actually bias. The bias match this kind of little 1 over here. So, and this is going to be +1, -1, +1, and this will be 1 -1 +1 is 1. 0 -1 +1 is 0. 0 -0 +1 is 1. This is how we could combine across feature to obtain a new set of features, 101. And then we can repeat this process one more time. What about this one? This time, I get this and this. So map to the second and the third row in this case. And there's no bias and also force weight. This actually is 0, can ignore. So this will be my +1 and +1 over here. And so this empty cell will be the result of adding these 2 rows up. 0 + 1 is 1. 1 + 1 is 2. 1 + 0 is 1. So this similar process. Hopefully you appreciate this contrast, trying to contrast between the way you combine across features, also combine across positions. In the yellow matrices, then my favorite color to represent all my example I've been sharing. I use yellow to represent attention. I use this red ones, border one to represent weights and biases. And so now we can do the both. How do we combine both position and features in this case? So then we just put the attention matrix to the upper right and the weight matrix to the lower left at the same time, but I can stack them so they can be computed in a sequence. So in this case, so you follow a similar logic for this one, 1, 1 will map to these 2 rows. I mean, 2 columns. And the result is just combining these 2 columns, 1, 1, 1, 0. These are already computed for you. Now, once I have this, now we have, again, then we follow with this process. This and this and this map to this and this and this. And it's plus 1 minus 1 plus 1. And you just add these 3 rows, but remember to minus the 1 in the middle. So you get 1, 0, 1, which is the same number up here. So you can just repeat this pattern. This is the same thing as above, to more condensed. And I could just give you another rundown by you're going to go get the same number 1, 1, 1, 0 as a result of combining this and this column. And for this one, it's going to be 1, 0, 1, the result of combining this column and this row, and this row. And now we have this blue one are the transformed embedding vector. You could compare that to the original. You have this kind of orange ones. These are how the embedding was just looked up from the table directly. And we feed into a transformer, combining across position and combining across features. We derive exactly the same set of 3 vectors, but they have embedded a lot more information. At the end, and then you combine it into a sentence embedding vector again by doing the average. So this 2 over 3, so it's a 6 over 3, and 3 over 3, and 2 over 3. Okay? So this is my 5 minutes quick overview of transformer. And then I will have some other materials about transformer on LinkedIn and or my other lectures. So if you're interested, you could follow them. But this is what I have. I do still have 4 minutes for question answering, and hope that there's a lot of questions. If I cannot get to all the questions, we'll send a follow-up email. All right. So I will turn my video on.
Thanks, Tom. Yes, there's been way more questions than we could ever answer here, but we'll definitely follow up with folks via email for all the questions that we don't get to. Akmal, I know you've been typing furiously over there. Do you see any great unanswered questions that you'd like to pose to Tom?
Yeah, well, I think, Matt, one common question, Tom, was basically how did you choose the vectors? So you have a representation of a dog, you picked 3 dimensions, okay? You got something for a cat, you picked some numbers. How did you arrive at that? I mean, is it something arbitrary? You decided, okay, are these the 3 numbers I'm going to use?
So we have a machine learning
or algorithm that you used.
So answer is there are some other algorithm you can take there will be a different topic about how you could get those embeddings. Since the focus of this lecture about vector database, when you actually work with the vector database, you usually assume this embedding is given to you. That embedding will help you convert words. And I believe last week there was a lecture about embedding. Maybe you can check that out. And today I offer you some intuition. You have 2 different embedding schemes. You can compare them and say one is better. And you change it a little bit, you can say, oh, am I improving or not? So this is the intuition behind training the embedding. So you're embedding a pre-train, keep repeating this process until you get a good one. Once you have a good one, you stick with it, and then you use, when you have a vector one, and then you started to build your vector database. At that time, your embedding is fixed. You don't want to change it anymore. If you change it, you have to reindex the whole thing. Hope that answered the question. And
Good stuff. I think we might have time for one more question before we do the raffle winner announcement. Akmal, is there another burning one or a trend that you've seen that you want to pose to Tom?
And then meanwhile, I have this question for everybody. What is a dot product of this?
Answers on a postcard.
Yeah, I don't know.
All right. So we won't lose these questions, right? After the session.
I see a lot of 14s coming in, a couple 15s, mostly 14.
Okay, cool. What do you think? What do you think? 14? I think the answer is 14. And if you type 13, it's probably a typo. Thank you. I'm really pleased to see all these responses. It shows that people are listening, and this can resonate with this content, and hopefully your hands not getting too sore. My hands kind of sore with a lot of stuff today.
Love it. Okay, let me quickly do one announcement before announcing the raffle winner. And Akmal, could you take over the slides and show or maybe it's the second slide. But
Yeah.
I just want to point out that if you like today's topic, we are going to be going further on this topic and more. The most imminent session is tomorrow's Claude 3 cookbook, leveraging OCR and multimodal data extraction. I just put the link in the chat if you want to RSVP, and hopefully we will see you again tomorrow. And let's go ahead and do the announcement you've been waiting for. Today's raffle winner is Luna Rajbandari, VP of Data and Technology at Cars.com in Chicago. Congrats, Luna. Thank you for joining. That's not you. Don't give up. We're going to give out one more raffle winner, your choice, either AirPods or the Meta Ray-Bans, to someone who has tried out this technology, that our vector database that we're showing off. So I'm going to put that link in the chat one more time. You just sign up at that link. You could be our next winner. Thanks so much, Tom and Akmal, for today's presentation, demo, and audience Q&A. Thank you to our audience for joining us. Have a great rest of your day. Bye, Tom.
Bye-bye.